Scalar vector multiplication. In calculating various quantities in physics, we sometimes encounter the multiplication of a scalar quantity by a vector. For example, Newton's second law, which states that the net force acting on a mass equals the mass multiplied by the acceleration of the mass motion. In this relation, the mass, a scalar, is multiplied by the acceleration, which is a vector. In such case, the result is a vector whose magnitude equals the absolute value of the scalar multiplied by the magnitude of the vector. As for its direction, if the scalar assumed positive, the result points in the same direction as the vector. If the scalar is assumed negative, the result points in the direction opposite of vector A. Now suppose A is a vector in space, and we want to obtain the vector 2 times A. In this case, the vector 2A has twice the magnitude of vector A, so we double the magnitude of A. And since the scalar multiplied here is positive, the direction of the result is the same as the direction of vector A. If we want half A, this is a vector whose magnitude is half that of vector A, but since the scalar is positive, its direction is the same as vector A. Similarly, we have minus 2 times A, whose magnitude is still twice that of vector A, but since the scalar here is negative, its direction is opposite of vector A. Or minus half A, its magnitude is half that of vector A, and its direction due to the negative scalar is also opposite of vector A. Dot product. Let's first examine the concept of work. For work to be done, a force must produce a displacement in the direction of the force. In that case, the work done equals the magnitude of the force multiplied by the magnitude of the displacement that occurs along the direction of the force. Now, suppose there is an angle between the force and the displacement. That is, the displacement is not entirely along the direction of the force. For example, suppose we have a force vector and the displacement vector with an angle phi between them. In this case, the work is obtained from the component of the force that lies along the direction of the displacement, or the component of the displacement along the direction of the force. So in this case, we must project the force onto the displacement and obtain its tangential component. We previously discussed vector decomposition. In this case, the displacement multiplied by the tangential component of the force along the displacement determines the amount of work. That is, delta W equals to F sub t times magnitude of dl vector, where F sub t is the tangential component of the force along the displacement, obtained from the relation F sub t equals abs F times cosine phi. Substituting F sub t, we got delta W equals abs F cosine phi abs dl. This quantity actually represents a type of product. Call it the dot product. In general, if two vectors have an angle between them, for example, vector A and B with angle phi, then the quantity abs A abs B cosine phi is called A dot B, or the dot product of A and B. The symbol for the dot product is the dot. It's quite clear that if A is perpendicular to B, that is, if the angle phi is 90 degrees, the dot product becomes 0. So if A dot B equals to 0, this means the two vectors are perpendicular to each other, and if two vectors are perpendicular to each other, their dot product is 0. Now, if we reverse the order of multiplication, that is, instead of A dot B, we look at B dot A. In this case, we must project vector B onto A and multiply by the magnitude of A. So we must go through the trigonometric angle minus phi. We got abs B abs A cosine minus phi. However, cosine is an even function, so cosine minus phi equals to cosine phi. As a result, B dot A equals to A dot B. Therefore, the dot product has the commutative property.